Section 10.3, factors that affect solubility. Some factors that affect solubility are structural effects, like we saw, polarity, which is related to structure, can affect solubility. We can have an effect because of pressure. So the greater the pressure, the more gas you can dissolve in a liquid, for example. And then temperature effects. Right? You guys have all probably tried to make yourself some sweet tea, and so you know that you mix that sugar in when it is hot, and you get a nice saturated solution, and you can dissolve more sugar when it is hot. So we know that there are some temperature effects with dissolving a solid in a liquid. There's also temperature effects when we're talking about dissolving a gas in a liquid. And that's very important if you're doing marine biology or oceanography, the idea that you can dissolve a gas in a cold liquid more efficiently. So let's look at some structural effects. Molecular structure determines polarity. Right? If the solute and the solvent have similar polarities, solubility is favored. Nonpolar substances are described as hydrophobic, water-fearing, so for example, vitamin A. Polar substances are described as being hydrophilic or water-loving, so for example, vitamin C. That's why a lot of vitamin supplements are really just expensive urine pills in the best case. In the worst, you can get a lot of fat-soluble vitamins, A, D, etc., that are going to stick around, mainly accumulating in your liver, and that can lead to some serious adverse health effects. So if you're ever on an Antarctic expedition, don't eat too much sled dog liver. Right? And then there's a URL to follow up on that. So let's look at some of the structural effects of solubility on vitamins. Vitamins, like we said, can be divided into two classes. Fat soluble, those are our nonpolars, A, D, E, K. So vitamin A is virtually nonpolar, composed of mostly carbon and hydrogen atoms with similar electronegativities, and thus soluble in nonpolar materials such as body fat, but not in polar solvents such as water. Water-soluble vitamins like B and C, right? Vitamin C is going to have many OH groups and CO bonds, making that molecule polar and thus water-soluble, which is why a lot of vitamin supplements, like I said, are just going to be expensive pee pills. Right? You're going to see that bright yellow urine from that vitamin B that you've been taking right away. It's not going to stick around. Your body's going to flush that out pretty quickly. Taking a look at the structure of these two molecules, right? Vitamin A has this long conjugated system. Right? It's got this very greasy backbone where you've got a series of carbons in a chain. So it's going to be very nonpolar. It's got a little bit of polarity, right, from that OH group at the end. But compare that to vitamin C. Vitamin C has the ability to hydrogen bond all over the place. So the circles indicate where polar bonds are. The vitamin C contains far more polar bonds than vitamin A. Pressure has a very little effect on the solubility of solids or liquids, but it significantly increases the solubility of a gas. If the pressure is increased, the number of gas molecules per unit volume is going to increase, and the gas enters the solution at a higher rate than it leaves. So we're pushing things out of equilibrium. If we're increasing the pressure, it's going to strive to reach a new equilibrium pressure, but the concentration of gas in the liquid is going to be higher. Right? As the concentration of dissolved gases increase, the rate of escape of the gas also increases until that new equilibrium is reached, and the solution contains more dissolved gas than before. So this is not a perfect analogy, but you can think of this pressure as like smushing more of these gas molecules here into that solution. So in A, we've got a solute in equilibrium with a piston, right? Equal number of gas molecules are going up in green as they are going down in red. As you compress this piston, the piston is pushed in, it increases the pressure of the gas and the number of gas molecules per unit volume. So more start to go down into solution. The greater concentration in the solution causes an increase in the rate of escape, and they're going to balance each other out, with the net effect of being that you've got more gas molecules dissolved in that solution. And is there a quantitative way to describe this? You bet there is. That's called Henry's law. And it's going to give us the relationship between gas pressure and the concentration of dissolved gas. Real simple. It says that C is equal to Kp. So that our concentration of our dissolved gas is equal to the pressure times some fudge factor K that makes it all work. So our concentration could be in moles per liter. It depends on what the units of K are. Our pressure is usually going to be in atmospheres. And K is going to be unique to each gas and solvent system. So K is going to change if you go from carbon dioxide to oxygen, dissolving it in water, and it's going to be a different value if you're looking at oxygen dissolved in water versus oxygen dissolved in, say, ethanol. But it's going to say that the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. Right, let's look at an example. So we've got a soft drink. It's bottled so that at 25 degrees C, a little bit above room temperature, it contains carbon dioxide at a pressure of 5 atmospheres over the liquid. Assuming the partial pressure of carbon dioxide in the atmosphere is 4 times 10 to the minus 4th, this would be a number that they would give you. Calculate the equilibrium concentrations of CO2 in the soda both before and after the bottle is open. So we got a two-step process. What is our concentration before? What is our concentration when that gas is allowed to escape and the pressure goes to 1 atmosphere and not 5? The Henry's law constant, that would be something they would give you. You have CO2 in an aqueous solution is 3.1 times 10 to the minus 2 moles per liter times atmosphere at 25 degrees C. So let's do the first part. If we know that our concentration is going to be K times the pressure, and we know that our K for carbon dioxide is 3.1 times 10 to the minus 2 liters per atmosphere, we're just going to look at this at 5 atmospheres. So now we've got our K. We've got P. All we need to do is multiply those two together times, right? 3.1 times 10 to the minus 2 moles per liter atmosphere. Our atmospheres will cancel each other out. There's one on the bottom and one on the top. And we're ending up with units of moles per liter, or our good friend molarity, 0.16 moles per liter. Once we open the bottle, if we open the bottle, it's going to reach an equilibrium with the atmospheric partial pressure, 4.4 times 10 to the 4 times 10 to the minus 4 atm, because one atmosphere is made up of our atmosphere is made up of many different gases, carbon dioxide being a small portion of that. So we've got a new pressure. Did we have K from before? We sure did. So we're going to do 3.1 times 10 to the minus 2 moles per liter times atmosphere. Atmospheres cancel out. We end up with 1.2 times 10 to the minus 5 moles per liter, or molar. It's a significant change in the concentration, right? We went from 0.16 to 1.2 times 10 to the minus 5, so about 4 orders of magnitude difference. That's a significant change in the concentration of CO2, and that's the reason why soda goes flat after being left open for a while, right? It's going to reach equilibrium with this atmospheric pressure. Under pressure, right, it's dissolved a bunch of that gas. In atmosphere, the overpressure is only, or the partial pressure is only 4 times 10 to the minus 4. It's going to reach that 4 times 10 to the minus 4, a lot less fizz, and your fizzy drink. See? Mysteries of the universe are being explained in your chemistry class. Temperature effects. If I take a solid and I dissolve it, it's going to occur more rapidly at higher temperatures. So the amount of solid that can be dissolved may increase or decrease with increasing temperature. So it's going to happen more rapidly. The rate is going to be faster. But the amount usually is going to be more, but not always. We'll check and see one of those exceptions in a second. Although the solubility of most solids in water increases with temperature, the solubilities of some substances will decrease with temperature. This temperature dependence is only determinable by experiment. Right? You can't look at something and go, oh yeah, that guy's going to decrease solubility with temperature. And so let's take a look at this. Right? So here is sugar, our good old friend sugar. So as you increase the temperature, you're going from 0 to 100, almost boiling. The solubility is going to go up. Right? So you can get a lot more sugar in water, right? 300 grams versus only about 180 if you go from 0 to 80 degrees, or 0 to 60 degrees. Right? Some things are going to be relatively flat. Okay? So this sodium bromide here, NaBr, is pretty flat. Some things are going to decrease. The cerium sulfate and the sodium sulfate are going to decrease as you increase the temperature. But again, you cannot determine just by looking at something whether or not it's going to drastically change solubility like sugar does, or potassium nitrate would, right? Or if it's going to be relatively flat like the sodium bromide, or whether it's even going to decrease like those two sulfates. Right? Most become more soluble, but that sodium sulfate and the cerium sulfate are less soluble. So, question, if I asked you guys, what is the solubility of potassium nitrate at 60 degrees, could you tell me? All right, so here's potassium nitrate, KNO3 line. I'm going to go to 60 degrees. Can you read this off, right? Looks like it's about 120, right? What if I asked and said, what is this in terms of molarity? Could you do that? Notice this is in grams of solute per 100 grams of water. Could you figure out what that is in moles per liter? Could you figure that out in mass percent? Could you do that in terms of molarity? Remember to look at what that bottom unit is. Mass percent, all the things. Molality, kilograms of the water, right? Molarity, moles per liter. Right? So that's a good thing that you want to be able to do. Okay. And like I said, that line up there explains why there is a right way to make sweet. And continuing with our temperature effects, the solubility of a gas in water is going to decrease as temperature increases. If you think about what the relationship between the temperature and the volume of a gas is going to be, that's Charles' law. So as you increase temperature, the volume wants to increase. That gas is going to try to get out of that solution. That's a way to think about it. It has important environmental applications because water from lakes and rivers is widely used in industrial cooling. So if you've got hot water, is that hot water going to be able to hold as much dissolved oxygen? Indeed, it is not. So you've got an oxygen poor environment. That's not good for sustaining things like animal life, fish. So if you're looking for a rich fishing area in the ocean, you're looking for places where that deep current is carrying up cold water. It's an upwelling. It's oxygen rich. It's going to provide more of a basis for life to thrive. So water is returned to its natural source at a higher than ambient temperature, and that leads to what's called thermal pollution. The warmer water has a lower concentration in oxygen and is less dense, tends to float on the colder water below, blocking normal oxygen absorption, and this affects aquatic life in the deep layers of a lake and in the ocean. We said Henry's law, that value for K is going to be different. So if I look at methane up here, its solubility as a function of temperature is going to be different than, say, oxygen or carbon monoxide or nitrogen or helium. The solubilities of several gases in water as a function of temperature and a constant pressure of 1 atmosphere above solution. The takeaway from this is those solubilities are going to vary with what the composition of the gas is as well. You'll notice that helium does not have much of a change in there, right? Helium is pretty darn close to our ideal gas. Something like nitrogen is also ideal-like, and then you start getting deviations where you would expect to see those van der Waals approximations come into play. Okay. Continuing, decreasing the solubility of gases with increasing temperatures also responsible for the formation of Boiler's scale. So if you look at old pipes, so for example, if you take an upper level lab in Bueller Hall, you're going to start to see some of this Boiler scale. It is just crusty stuff that starts to form on the inside of pipes. The bicarbonate ion is formed when carbon dioxide, which is all around us in the air, is dissolved in water containing the carbonate ion. So you got CO3 aqueous. It's going to react with dissolved CO2 and water, and you're going to form two HCO3s. If your tap water also contains calcium, so if you're in a place that has a lot of kind of hard water, so say it's been going through limestone, say if you're in the Appalachian Mountains, well, then that water contains some calcium ions. Those calcium ions are able to react with the carbonate and form calcium carbonate. Right? Calcium bicarbonate is soluble in water, but calcium carbonate is not. So when the water is heated, carbon dioxide, this gas, goes away. Its solubility decreases, leaving behind our calcium carbonate. For the system to replace that lost carbon dioxide, the reverse reaction has to occur. We're going to take our two hydrogen carbonates. We're going to make water, CO2, which is replacing the CO2 that was driven off, and some CO3 2 minuses, some carbonates. This reaction also increases the concentration of carbonate ions, causing that solid calcium carbonate to form. This solid is the boiler scale that coats the walls of containers such as industrial boilers and tea kettles. So if your tea kettle has some crusty, nasty white stuff on it, it is probably calcium carbonate. It's bad because it reduces the efficiency of heat transfer, and you can block pipes. So what we got here is a picture of a particularly nasty pipe. It's got accumulated mineral deposits. Most of those are going to be probably calcium carbonate. This cross-section clearly indicates reduced pipe capacity. So this is something that you have to think about if you're going to go into chemical engineering or if you are looking at civil engineering. So this thing that looks like the clogged artery, right? If that's the pipe carrying water to somebody, it's going to have a reduced capacity. If this is in your factory, you got to consider what is the actual volume that you can move through this. Fortunately, this is pretty easy to deal with. You just add in some acetic acid, some vinegar. It'll dissolve that right up, make a nice little